Hello, guys. Okay, so let's see. Let me load the PowerPoint slides for today and a couple of announcements, I suppose. One thing that we are. Hi, how are you guys? So one thing that we're going to start working on or doing, this semester, I'm going to be giving you questionnaires so you can practice. I mean, these questionnaires are not going to be graded. I mean, you're going to get a grade in the sense that you will get to see the answers. These are multiple choice questions, right? So you can just, I mean, most of them, if not all the questions, are going to require for you to just, think, run some calculations. It's not just simply, oh, I don't know, A, B, or C. So think about them. You will get to check if you got the right or the wrong question, right? And we can talk about those during the office hours too, for example. The idea again is that you have, some material that you can use to check if you're properly understanding some of the most basic concepts. You are going to have, remember, the homeworks, which the first one is coming really soon, right? Because we're wrapping up with ultrasound, and then you'll have your first homework. You're going to have some homeworks where you're going to be able to test, right? I mean, if you got some of the key concepts, and that's another thing that you're going to have, but at least this will help you, check if you're going on the right track or not, like in the sense of are there things that maybe you're not properly understanding, right? And you can ask, and that's kind of the idea, right? The other thing that I wanted to let you know, well, there's a couple of things. You have already the announcement for our first invited lecture of the semester, which is coming from Johns Hopkins University. And it's from an old friend, back when we were students, the 2000s, Mujinatu Bell, who got her degree in Duke University, and then moved on to several institutions around the world, in the US and the UK, and is now an assistant professor, an assistant professor at the Johns Hopkins University, which is, one of the best universities in biomedical engineering worldwide. And she is going to talk about ultrasound imaging with deep learning, which is she's one of the researchers that is, pushing for that trend. So you're going to probably learn quite a few interesting things. She also works in photoacoustics for those that are interested. So be there, and ask tons of questions. That's sort of the idea, of having this invited lecturer, so you can ask tons of questions. She is also, like from my point of view, right, one of the top female researchers in the world. And that's also important, because if you look left and right, like engineering in general is for everybody, right? For whatever reason, which I don't understand, was typically, a male-dominated field, which sucks because there's really no reason for it. Biomedical engineering is one of those fields where the split, is closer to 50-50. So again, look left and right, and you will see that there are several females among you, which is good, right? And I think it's really important that, just because that's the way it is, that you get to see role models that are representative, right? And I think she's a great speaker also. So I'm really sure you're going to have a blast. The second speaker, that we need to confirm the exact date, I think you're going to enjoy that lecture too. because it's coming from industry, right? And it's coming from a company that is, this is going to be the talk for tomographic imaging. And it's coming from a company that developed the concept of, it's actually related to ultrasound in a sense too. This is ultrasonic tomography. So you can actually do tomography with ultrasound, right? I mean, you can, just like you would with MR, you know, or with X-rays, you can do it with ultrasound. And it's a fascinating story, you know, how these things started in the Mayo Clinic laboratories, you know, back in the 70s, with people having this crazy idea on how this could be done in a road that took, you know, probably like 40 years, you know, from that first notion of an idea to a technology that was robustly implemented. And from a scientific point of view, the trip is just amazing. In making it into a product that's commercially viable and that is now FDA approved for use in breast cancer screening and diagnosis in the US. So it's, I think it's just fascinating, you know, the things that you can learn from people in industry in general, right? Not to have, you know, just professors telling you about, you know, how great it is to write papers with master students or stuff like that, but, you know, how you actually build something, right? And sell it, and the things you have to think about. So I think you're going to enjoy it a lot, crossing fingers I'm not wrong about that. And then I will let you know about the other speakers as, you know, time goes by. But I mean, just over there, I'm pretty happy how these things are starting, you know, with one of our top female scientists in biomedical ultrasound, and a talk coming from industry, you know, from something that's revolutionary in the way that we do medical imaging from my point of view. So, I mean, we're coming off to a good start. So with that being said, we can actually start with today's lecture. And just so you guys know, I'm seeing that we have 17 people here. Don't get me wrong. I'm happy with whoever wants to come and ask, but I would really, really, really encourage you to tell your friends to show up, not because my feelings are hurt if you don't come, but technically speaking, like I could just upload the slides to the Paideia site. You can read them all, you know, and you can hand me over your project by the end of the semester and solve the homeworks and we're done, right? I'm assuming that like the idea of having this is that you can ask questions. That's the idea of having lectures. You have textbooks and stuff. Nowadays, you don't need me, you know, to learn the basics of things. So take advantage of that. Just, you know, be smart. Okay, so with that being said, let's go to week 5 and we can talk about, we can start talking about actually, because this is going to take a longer time. We can start talking about Doppler imaging. As I mentioned to you, you know, I also left you a few slides that I'm really not going to spend more than probably 5 minutes talking about today, because you can actually read them or like watch them on your own. The slides have to do with just echographic imaging, you know, a rough idea of, you know, what it is. And this is a fairly incomplete, you know, description of things, mind you. And just to cite a few things, right? Obstetric imaging is probably one of the key applications of echographic imaging. The reason being that biosafety, right? We are talking about neonates, or we're talking actually not neonates, but we're talking about, you know, fetus. So these tiny unborn babies, you know, are very delicate. They're very sensitive to many things because they're in their earliest stages of development. And we don't just irradiate them with X-rays, you know, we just don't do that. And magnetic resonance imaging, you know, even though it's relatively safe too, it's just too slow, and many of it's just too expensive. Ultrasound is amazing because you can actually see the anatomical features. You know, you have enough resolution to look at like a really, really tiny little unborn baby in there. But eventually also you get some functional imaging that's very needed to monitor the obstetric development, like the cardiac cycle, right? The development of the heart. And that is basically what we're going to be focusing on, not necessarily for obstetric applications, but just in general what Doppler imaging is. Okay, so we're going to start talking about this during this lecture. But that's not the only thing that we can do with ultrasound, right? I mean, here's an image of a breast on the top left, and then the image of an eye on the top right, and there's a kidney, although it's an ex vivo kidney, so that's probably not very impressive, on the bottom left. And we even have like an image of a skin tumor on the bottom right. So kind of the idea of this, you know, is highlighting that, yeah, of course, we have things like, again, the female breast, right, which ultrasound is very commonly used as an adjunct technique to mammography. It's typically not used for, you know, screening, because the area under the curve would be pathetic, but it's just as an adjunct for diagnosis. Okay, and there you can see, you know, there's a whole organ, things like that, and you know, at frequencies that are roughly like in between like 10 megahertz or something. So these are things that are easily understandable that we can do. Maybe not a lot of people know that you can do, you can create images of the human eye. You can do that also with optical coherence tomography. But for ultrasound, it works like a charm. You can go very, very high frequencies and do this. Just like you can do images of the skin, right? I mean, the skin is really thin. So it took the advent of high frequency ultrasound. And by high frequency, we're talking about, you know, 20 megahertz and above. Quite likely probably even 30 megahertz and above in order to be usable, you know, but it's good that, you know, you can do it. And if we're thinking about imaging of the kidney, we're thinking abdominal imaging. We're thinking abdominal imaging, we're probably thinking more something like this, right? I mean, this will be an image with a curvilinear array, and you get to see that, you know, there are dark structures over there. There's like a tree-like structure, which, you know, I don't know if you know what that would be, but you also see vessels, you know, arteries, veins. You see those dark, like, I don't know if to call them circles, it's like an ellipse, right? That has a very bright rim on the top and on the bottom because of the reflection of the ultrasound. And it looks very, very dark, right? So you just keep that in mind, because that's going to play a role when we talk about Doppler imaging later on today. But yeah, and again, you see that's like the liver, right? And you get to see the edges of the liver down there, you know, it's like a really big organ, you know, that the liver is massive actually in your body. And ultrasound is very commonly used, you know, for assessing things like hepatic steatosis, which is very commonly, you know, the first thing that you would do. You just take a son before you know, get a biopsy or something. If you see that the liver is abnormally bright, or if attenuates a lot, then you kind of know that the person has a fatty liver. For fibrosis, it's hit or miss. For fibrosis, you would probably, if you want to do something ultrasonic related, it would be elastography. And we'll get to talk a little bit about that probably in the next lecture. Yes, we have a question in the chat. Is it like an anechoic chamber? No, actually an anechoic chamber would be a place where you take measurements, right? Like an anechoic chamber is a chamber, like a measurement chamber, where you don't get multiple reflections actually, right? So you can like have a source of whatever radiation, right? Acoustic and ultrasonic radiation, and it will go around the chamber. But when it gets to the sides, like the walls of the chamber, you will get things that fall back. So you can maybe characterize sources, right, with hydrophone and stuff. So that's what an anechoic chamber is, and they're really kind of difficult to put together actually. But yeah, no, that has nothing to do with anatomy whatsoever. Like maybe you're thinking of something else, but just terminology-wise, that has nothing to do with anatomy. Thank you for the question. The gallbladder, you know, is one thing that maybe you don't know that as you get older. But I don't know. I mean, I thought of myself like a really old person by the time I became 20 anyway. But anyhow, as you get older, you will get to see more and more people that have problems with their gallbladder, and maybe they will need to have the gallbladder removed. That's probably when you hit, you know, your 30s or something like that. You will get to see that a lot. So it's a spoiler alert from your life from now on. For a lot of people, you know, and actually like one of our students in the laboratory once, like I had a female student who who had gallbladder stones, and it would look like the image on the left. It was not the image on the left. She sent it to another student who's a male student. It's like, what do you think? And the guy said something like, congratulations, because he thought that it was, a pregnancy echographic image or something like that. Truth to be told, kind of looks like a baby, right? I mean, it's like the little head and then there's a body, but that just goes to show beyond how moronic males can be, because you just don't say that. But anyway, it just gets to show you one thing about ultrasonic imaging, which is that it's very difficult to read the images. Because, I mean, fair enough, I could guarantee that if I show the image on the left to, that's just the general population, and I ask them what they're looking at, probably, 80 something, we should do that someday, just do that. But anyway, probably 80 something% of people would be like, that's a baby, congratulations. It's not, these are gallbladder stones. This is the, it's basically as a gallbladder, right? Which is the sac where the liver would, store the bile, right? That it needs to do what it does. And it's developing sludge at the bottom, right, of that sac. And that sludge eventually becomes the stones, which are not necessarily, you would think if there are stones, then you would go to X-ray imaging and you would see them, but not necessarily, because these are not typical stones. These are not calcified stones necessarily. So many times gallbladder stones are not visible with X-rays. So there's another thing for which, ultrasound is the king. It would be that. I will skip this one, thyroid imaging for sure. This was the realm of nuclear imaging many years ago, but with the advent of high frequency ultrasound is the king for the thyroid. The clinical management of the thyroid from a radiological point of view involves almost exclusively the use of ultrasound, even for things like the biopsies. The name would be fine needle aspiration biopsy, FNAP. You would guide the biopsy with ultrasound too. Okay, so I mean, very high resolution, and you can see the nodules, and the trick is to figure out if the nodules are cancerous or not. And I think I told you guys in the first lecture that the issue with this is that, I mean, the reason why this tool becomes important is because probably half of the population has thyroid nodules. Most of you will have them and you just don't know that yet, okay? A couple of things here and there, which maybe you can read, but I'll just take 2 minutes on this. It's actually shadow, it's not shade. I should correct that. But anyway, shadow and acoustic reinforcement. So if you look at these two images, which are super old, right? I mean, the one on the left, it's like a tumor, and then there is a shadow after the tumor. The one on the right is there's a tumor, and there's a bright things that are coming from underneath the tumor, right? It's a completely opposite thing, right? In one case, you see nothing after the tumor. In the other case, you see something really bright after the tumor. That is typically linked to the attenuation properties of the tumor, okay? So if the tumor attenuates more than the surrounding tissue, right, it kind of makes sense that ultrasound dies inside, the tumor, and then you get very little signal outside of the tumor. And at the same depth, maybe on the side, the ultrasound goes through just the regular parenchyma and it attenuates some, so you have more signal at the same depth, simply because the tumor ate it all, right? It's like the dog ate my homework. It's like the tumor ate my ultrasound signal, right? On the opposite side of the spectrum, when you have the reinforcement, is when the tumor doesn't attenuate anything. So maybe you have a fluid-filled cyst, for example, right? It's not water, but it really, I mean, it's mostly liquid and it attenuates nothing, right? So you have ultrasound, it goes through that, it doesn't attenuate anything for a few centimeters, and then all the signal comes out, and you have a very, very strong ultrasound signal compared to what you would have on the side, where, it's going through tissue, and you lost a lot of signal by the time that you made it to the same depth. So here's really bright, and here not quite so, right? So it's this acoustic, posterior acoustic features, which is the actual name, right? Posterior because it's after the masses, and acoustic features simply because, I mean, it should be something else, right? But you kind of get the point. They're basically linked to attenuation to a very large extent, okay? And finally, we talked about how, like the choice of frequency is related to the clinical application. If you want to look at a very big organ, you kind of have to use a low frequency. If you want to see something that's very deep inside the tissues, or inside the body, sorry, you would have to go to a very low frequency so the wave will propagate, with enough energy. And that's sort of a problem, in certain applications for which we have non-invasive, semi-invasive tools like transrectal ultrasound, which I think the name is pretty much self-explanatory, so I'm not going to go much deeper into that. But transrectal ultrasound is typically used for monitoring the prostate gland, right? Which prostate cancer is one of the top leading, cancers in the male population. So if you guys thought that, mammography was uncomfortable, and it's like, well, yes, it is, but, think again, because when it's your turn, it's not going to be fun. I mean, so I'm crossing fingers I never have to do that. That being said, probably the one that should be highlighted in here first would be transvaginal ultrasound, right? Because it's probably, when you really think about it, the first one that comes to mind when you're looking at fetuses in a very, 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 very early stages of pregnancy. They're tiny, right? So if you go transabdominally or transpelvically, you're not, I mean, it's going to go very deep. It's going to be a tiny thing. You have to go at frequencies that are very low. You're not going to see it clearly. So you want to go to higher frequencies. You have a transvaginal probe. You insert it, into the vagina, and you can have a much better depiction, right, of these glorious early days of pregnancy. Of course, there are things like IVUS, which is intravascular ultrasound. You have a catheter, you insert it into the artery, and you start to rotate it. It basically rotates an array or a transducer. I mean, just a small array that would be, and you get this polar view, right, of the lumen of the artery. And basically, you're going to analyze plaque, right, and you're going to be interested in looking at the different components, like the soft components and the hard components, and trying to hopefully understand if the plaque is going to be symptomatic or not, namely if it's going to break, and eventually cause problems like a stroke or something like that, or if it's going to just likely be there forever and ever, and you shouldn't be that concerned, And again, these explorations are done at a very, very, very high frequency, right? So that's, and that wouldn't be possible if you were to do it from the outside of the body. You can do it only because, you have catheter and you're kind of going in. So it's semi-invasive, right? I mean, it's not completely invasive. You're not cutting things off, but you have to insert the sensor inside the body by some means, right? So those are some of the things that are in your material. So just a quick overview of that. Now, let's talk about the main topic of today. And I would like us to make it to a certain point so we can carry on with the discussion, or the more involved discussion, on the next lecture. Today, I want us to look at continuous wave Doppler. I'm pretty sure we'll make it there. If you have, even a middle, of the line scanner, it will likely be able to produce, images like this. You get to see the grayscale image on the background. That would be your regular echographic image, right? Sorry, did somebody, I think Brenna was going to say something, or?
I was responding that yes, I can see it.
Okay, awesome. So you can see the anatomical image, right? That's the echographic image in the background. And then you see a couple of more things. You see a color image, and you see some really weird looking things in the bottom, right? That looked like an EKG. It's not an EKG, right? But I mean, you see that there's some signal goes up and down, up and down, up and down. The one in the bottom is a pulse wave. It's a pulse wave Doppler image. It's called an image. It's really not. Okay. But basically, they're in your, right, in the top panel, you get to see that there's a dotted line, and there's a cursor somewhere, even though the cursors are kind of difficult to watch. And in that gate, you know, that's selected by the cursors, you're going to process the data in ways that we're going to discuss somewhat today. No, actually not today, but the next lecture. You process them so you can obtain information about the blood flow, right? And you see it in those things that, I mean, they have this periodic or repetitive pattern because of the pulsatile nature of circulation in the human body, right? I mean, it's not like here goes the blood, right? At, I don't know, 1 meter per second, steadily going, right? That would be a river, that would be a water hose. That's not how your body works, right? Your heart is a pump that acts in a pulsatile way, right? Contracts, expands, contracts, expands. So the blood flow, you know, it goes fast and then it goes really slow and then fast and then slow, so on and so forth. I think we have a question in the chat. Yes, we have a question. So talking about high frequency ultrasound, who we know, please correct me if I am wrong, that more frequency we obtain better quality of the image with the counter of losing depth. Is there a way to avoid this, like an acoustic reinforcement? Yes, you're absolutely correct, Emilio. In effect, right, when you go to higher frequencies, you have a better resolution, you have a better beam, you have a shorter pulse, you can discriminate things better. The problem is that you lose signal like crazy, right? Let me see if I can do one thing. This is an interesting question anyway, right? Let me see. Here we go. So I think it's in here. Maybe here. No, not that one either. Maybe here. Okay, let me download it from here then. There is one thing, right, that I don't know if to call you that you can, I mean, I think it kind of addresses your question in the sense that when one, you know, deals with ultrasonic imaging and what are the things that we can do, right? Let me see. So it should be downloaded now. Okay. So let me share this in here. Okay. Can you see it?
Yes.
Okay, awesome. So this is a new, this is a paper that's called New Sonographic Techniques for Harmonic Imaging Underlying Physical Principles. You can actually find tons of papers that talk about this, okay? But the idea is that it's harmonic imaging, okay? And harmonic imaging is something really, really interesting, okay? So if you have a signal, right, like this, like the one on the panel A, it's like an oscillation, and the spectrum will be just, you know, like one delta function, right? That would be if it's like infinite going to the left, infinite to the right, that's just one signal, right? The one frequency component. If you operate an ultrasound scanner, right, it has an oscillation frequency, but it's a short signal, right? So what happens is that translates into the signal having a bandwidth, right? Which is something that we discussed already. Okay, so it's a short pulse. So you're going to have a center frequency, but you're going to have a bandwidth, right? The interesting thing is, if you actually, you guys remember, right, that when we talked about the wave equation, right, we said that we had the equation of state. The equation of state basically said that, for example, the relationship between the pressure and the density is an adiabatic process. And we linearized it, right? So that we could somehow have a linear equation that we could relate to the other equations we had and, you know, come up with a linear wave equation. And we said this linear wave equation is only valid for very low values of condensation, right? Fractional changes in density. Like if you're actually sending a signal that's very, very strong, so that it just expands and contracts the medium a lot, then things are not going to be that nice. And this is what ends up happening. When you send a signal that has very high amplitude, you end up generating harmonics. Okay, so you not only generate the signal at F naught, but you also generate it at 2 F naught, and at 3 F naught, and at so on and so forth. Now, the harmonics usually go decreasing in amplitude, right? So the one that we mainly care about, and the one that in practice only people cares about, is the one at 2 times the excitation frequency, okay? And that is actually very, very interesting. So I'm going to stop it in here. That's actually very, very interesting because what it means is that you have the capability of, you transmit, imagine this, right? You transmit signal at 5 megahertz, right? So making it all the way to the medium, you're transmitting 5 megahertz, and then you get to the part that you really care about, right? And you focus on that part. So your signal amplitude gets bigger, right? And that is going to generate harmonics because you're non-linearly distorting the ultrasound. Then you have signals coming back to your transducer, and those signals happen at 5 megahertz, but also at 10. So if you isolate the signal at 10, right, which there are algorithms that will allow you to do that, which are outside the scope of this, right? You can isolate the signal at 10. What do you gain? You gain so much. First, you don't have the attenuation going from the transducer to the region of interest and then from the region of interest to the transducer, right? Because the 10 megahertz component didn't generate at the transducer. It generated in the body at the part where you were focusing the ultrasound so that you will get a really large amplitude in the signal. So your 10 megahertz signal doesn't have a round trip attenuation. It only has a way back attenuation. So you effectively reduce the attenuation by half. The second thing that you gain, which is kind of really cool and awesome, right, is that imagine like if you're imaging through, you know, the abdominal wall of, you know, somebody who may not be like super thin and stuff. So you have an increased amount of body fat and maybe an enlarged amount of muscle, you know, in the abdomen. And then there's a lot of distortion in the acoustic wave, right? And if you actually have that signal, like it gets distorted all the way down to you know, the part that you care about, and then it comes back and it's distorted again, then overall the signal is severely distorted. But when you have harmonic imaging, because you know the signal actually again generates down here, the distortion that you're obtaining is mainly the one that you get on receive, which means that effects like phase aberration, clutter, and other things that have fancy names, and someday we can talk about them if you buy me a coffee or a beer or something, those get severely reduced too. As a matter of fact, many people wouldn't know that probably in clinical practice, but they're probably using the harmonic imaging mode rather than, you know, the standard imaging mode, because harmonics look so much better. Like harmonic imagings look so much better than their fundamental counterparts. So if I were to actually think about, you know, something that's implemented in scanners that a lot of people wouldn't know that's implemented in scanners, but probably, you know, their lives would be so much tougher as a sonographer if that wasn't there. It will have to be harmonic imaging. And it's a really cool principle, you know, it's like taking something that should be a negative, which is the distortion of the signal, the deviation away from our ideal and holy, you know, like wave equation that we made so many efforts into putting together, just using it to our advantage, right? So that's kind of neat. So I guess, you know, I don't know if that directly answers your question, right? But if your question was, you know, is there any way that we can obtain a better image quality, you know, like using physics to our advantage, you know, so that we can get, you know, better signal at higher frequencies coming from deeper, probably the thing that comes to mind would be harmonic imaging. Hopefully that addresses your question. You're welcome. So, Breno, yes.
Yeah, in that case, teacher, how would the technician measure the trade-off between having because you say that the harmonics will have less amplitude in the end anyway. Like,
Right.
I mean, there
The
will be,
harmonics, the second
yeah,
harmonic signal will always be a fraction of what you sent, right?
yes.
That's for sure. But typically in ultrasound, right? I mean, what you actually want to have the high amplitude because you want the signal to be clean. But because the signal is so much less distorted, you know, it's not only that it has a better resolution, but it has less distortion, you know, from the propagation from the transducer down to the region of interest, you know, that portion of it. So you have reduced clutter, reduced aberration, reduced many other things. Then the quality of the overall signal is better. And that's typically why it in general just looks better, you know.
Okay.
And yeah, like with everything, you need to know how to use it. But many times, you know, I remember, like, for example, you remember that study with the kidney data, right? And I remember getting the echographic images from the kidney. They look beautiful, you know, and then they sent me the raw data and I was like, there has to be something wrong because we're processing the data, we're filtering it, you know, we know that, you know, the signal, the images from the scanners typically look better than what we process in-house, but our images look like crap. And the images from the scanner look fantastic. And we didn't know why. And it's like, oh yeah, but we forgot to tell you the ones from the scanner are harmonic images. It's like, okay, fine. I mean, because I already knew, like, if they had told me earlier, then I wouldn't have worried. But the point is, it's really that different, you know, because again, you have to understand, not only you get the better resolution, you get the better distortion, even if the SNR, the electronic SNR is like, quote, weaker, we can always compensate for that. I mean, we have really good amplifiers in a high rate scanner, you know, to compensate for that. So they look much better, much better.
Okay. In any case, is there a limit for how deep can we go with harmonic images, or can
Oh
we
yeah,
go?
there's limits for everything, right? Because I mean, in the end, you cannot send a pulse that would be so strong that you would be ablating the tissue, right? Which
Yeah.
you can also do. You can ablate tissues with ultrasound, right?
Yes.
So there's a limit to that. So there would be a limit on how deep you can go. There's limits to everything, right? For sure. I mean, this is not an overall like universal solution that will allow you to do anything, but it will help you stand the trade-off, you know, in between how deep you can go and the quality of the overall image, you know. Even if going deeper, you know, wasn't like what really of a concern, just the overall quality of the image looks much better. And again, I mean, it's unfortunate, like many of you guys will know already, that this is an introduction class, you know, so there are so many topics that we just simply don't have the time to go deep on them. But I mean, at least we can motivate the discussion, right? So here we go. So anyway, going back to flow velocity estimation, right? You have the pulse wave Doppler on the bottom, and then you have that color image on top, overlaid on top of the echography, and that would be the color flow image. In this case, in the classical, you know, overlay of a color flow image with the red and the hue and the blue hues, right? That's showing you the direction of the flow, right? Depending on it being red or it being blue, and depending on the actual hue of it, it tells you, you know, how fast it's going, and it tells you about the turbulence, and there's a whole color coding for this. But it's probably recognizable for, you know, the ones that have seen a color flow image in the past. But that's basically telling you how fast the blood is flowing inside the vessels within that particular region that is being analyzed. Okay, in this case, it would be a renal artery. So if we want to actually, you know, understand how this works, and again, this receives the name of, you know, Doppler imaging overall, and it's kind of funny because when we get to the actual algorithms that are used, you know, for Doppler imaging, you will see that they have absolutely nothing to do with Doppler itself. Okay, but they still got the name anyway. Do you guys remember what the Doppler effect is? You probably do, right? But I mean, just humor me. What's the Doppler effect?
It's the shift in frequency because of spatial variation.
Is a shift in frequency because of, okay, spatial variation. What do you mean by that?
Like when you are relative movement, that will be
correct.
Better, yeah.
It's a relative movement. When the transmitter is moving relative to the receiver, or the receiver is moving relative to the transmitter, or both, right? Correct. That's roughly the idea. So in the case of ultrasound, right, this is something that was, I mean, the first person that figured out that there was a Doppler effect to be measured at, you know, when taking ultrasonic measurements from vascular system was a Japanese scientist back in the 1950 something, you know. And that was published in the Journal of the Acoustical Society of America, if I don't recall this incorrectly. But this was done, you know, like in much simpler ways, probably very akin to, you know, some of the things that we're seeing here, which again have absolutely nothing to do with the way that we process, you know, blood flow information with ultrasound systems nowadays. And it was truly linked to the Doppler effect, okay? So in the good old days of just laboratory setups, of course, you could have your transmitter and your receiver separately, right? But in devices that actually would use Doppler measurements with the actual Doppler effect, you have, you know, you have them, maybe you have an array and you split it in two. So you have one beam that's a transmitter beam and one beam that's a receiver beam, right? And the reason for this is that you're truly really going to, you know, hit it like it is a continuous wave measurement. Right? The transmitter is going to be transmitting for a very long time. The receiver is going to pick up on the signal that comes back, right? You are going to set up the transmitter and the receiver in a way that their beams are going to intersect one another, because otherwise, then, you know, you wouldn't get any signal, right? I mean, you're going to get echoes only from places that are illuminated by the transmitter beam, right? And you're going to receive signals only from places that are illuminated by the receiver transducer beam. So they have to intersect at some point. And from there is where, you know, you get your signal and stuff, right? So they're usually going to have a small angle, right? But I mean, you sort of kind of, when you, for the simplified assumption, you can think that they're sort of parallel. So, you know, angle, and that the angle is the same. And they're both going to have, or they're going to be at an angle with the vessel that you're interrogating anyway, right? Now, when we think about measurements from vessels, we have to think about, in general, scattering from blood, right? And we have talked about, you know, scattering in tissues and how, you know, different cells or aggregates of cells can produce the scattering going back to the transducers. Like otherwise we wouldn't get, you know, signal from within the tissues. And the same idea happens when we talk about the scattering from blood. The thing is, blood, what it is just the plasma, right? And there would be cells suspended in it, like the red blood cells and the white blood cells, right? The vast majority of the structures that you're going to see in the blood are the red blood cells. And the red blood cells are these tiny oblong ellipsoids, right? It's like a disc, right? To a very large extent, it's like a disc that is very, 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 very tiny, you know, just like a fraction, like a couple of micrometers in size or something like that. We're talking really, really tiny things. Remember that, you know, when you have ultrasound, the strength of the signal that you receive back to the transducer also relates to the size of the structures that are scattering back. So if you have structures that are super mega tiny, you know, like let's exaggerate and say 1 micrometer, right? You would need, in order to have a strong signal coming back, you would need the structure to be roughly in the order of at least a wavelength. At 1 megahertz, you know, the acoustic wavelength is 1.5 millimeters. At 10 megahertz is 150 micrometers. At 100 megahertz is, and you kind of get where we're going with this, right? So actually it would take a ginormous frequency for you to, you know, have a wavelength that would be effectively interacting with red blood cells. Okay, and that's sort of the reason why when you look at vessels in conventional ultrasound images, for example, the transabdominal one that we were looking at, the frequency is so low that, you know, the wavelength is so large compared to the red blood cells that the scattering is minute. the signal that comes back from the blood is really, really weak. So weak, you know, that if you actually analyze at the amplitude only, it looks black. It looks like there's nothing in there. But it's not completely black. If it were completely black, then we wouldn't be able to produce Doppler images. The beauty of this is that the signal is weak, but it's there. Okay, so that's one of the reasons why, you know, Doppler imaging is very, very, very complicated to do. Like if you buy a really cheap, you know, Chinese made, but not like China, like top China, but China, like cheap China made ultrasound scanner, it can probably produce echographic images, but if you're, you know, guessing that you can get Doppler images from their side, that's never going to happen. And it just doesn't happen because you need really good instrumentation. You need really clean amplifiers, you know, you need really clean, you know, good looking transmitters that would send a signal that you can actually receive, amplify, and process. And that's going to be a really weak signal. You need a huge dynamic range. So, you know, really cheap scanners are just not going to make it. So you need something a little bit more expensive than that. Now, we know that the Doppler effect tells us that the Doppler frequency is going to be equal to the frequency of the transmitted wave multiplied by C plus the velocity of the transmitter divided by C plus the velocity of the receiver, right? And like sort of kind of, right? So VT for our case, it would be the speed of the reflector relative to the transmitter, and VR is going to be relative to the receiver, right? With the convention of signs in there. Now we're assuming that VR and VT are both much less than C, which certainly is the case. You guys know, for example, you guys remember more than know, what is the maximum value of the blood flow speed that you can observe in humans, roughly? Like don't tell me an actual number, like I don't know, like 1.34567, right? But you know the ballpark value of it.
Not really.
Crap, I mean, guys, come on. I'm pretty sure I shouldn't be able to go to your biomedical engineering professors to tell you that and tell them that, but yeah, that sounds bad, guys, I have to say. So basically we're talking about just a few meters per second, right? I mean, the most exotic of cases, you know, it would be like 2 or 3 or something like that. Again, it's a ballpark, right? We're not saying that's the absolute limit to what it is, but you know, I mean, it's typically, you know, 0 point something, 1, 2, like 3 would be like a lot, you know, but I mean, typically not much more than that. And that you compare it to, you know, 15, 40 meters per second. And yeah, I mean, for sure, that's even less than 1%, right? That's nothing. So that approximation is certainly valid. I mean, it's probably not even an approximation. It's just, you know, what it is. So if that's what it is, then we can do this. And again, we do Taylor series expansion, right? Because we know that 1 divided by 1 plus x, when x is really small, approximately equal to 1 minus x, right? And again, that comes from Taylor. So you can actually express Doppler frequency like f naught 1 plus VT divided by C, 1 minus VR divided by C. Again, VT divided by C is like a tiny, tiny fraction. VR divided by C is another tiny, tiny fraction. So when you expand that product, right, the fourth term that's missing in there is actually VT times VR divided by C squared. That thing is going to be negligible. I mean, you can seriously, I mean, not even think that you had it in there and carry on with your lives. And this, again, even though it says approximate, is like really, really, really a super good approximation, okay? Now, if we look at this, you know, from the graph here, we have, you know, the schematic. This is just a cartoon, right? And there would be a red blood cell, which it doesn't look like one because first it's not red, second it's not oblong, but you're gonna get the point, right? This is something moving. So you can see that VT is minus V cosine of theta. We're projecting this, you know, to the axis of, you know, the propagation of the red blood cells, which we're assuming that they're flowing, you know, together with the wall of the vessel. Of course, I mean, the blood would go like this, like it's flowing in a tube, which is a pretty good, reasonable assumption anyway. The VT would be minus V cosine of theta. This is going away from the transmitter. right? And because of the convention that we're talking, you know, the BR would be V cosine of theta, you know, because it's going away, but, you know, but you hopefully you understand why, right? Remember, in one case, it's a transducer, the one that produces a wave, right? And the receiver would be the red blood cell. In the second case, it's the red blood cell, the one that produces a wave, and the transducer is the one that receives it. That's why the convention in science is different in there. Okay? So when you do that, the Doppler frequency is approximately going to be, you know, F naught, the original frequency, multiplied by 1 minus 2 times V cosine of theta divided by C, which is the sound speed, right? And again, theta is the angle between, you know, the axis of the overall, you know, transducer arrangement relative to the vessel. Okay, so that's what it looks like. And the total Doppler shift, right? I mean, if you were to, again, receive the signal, look at the spectrum of the received signal, and you could measure the shift, right? Typically, these devices would operate with demodulation. So they would demodulate with F naught back to the baseband, right? So hopefully you guys know what I'm talking about. Is carrier modulation, right? I mean, you know from your properties of the Fourier transform, if I have a signal and I multiply it by a cosine, it moves it up to, or a sine, right? It moves it up to, you know, the center frequency being F naught. Like converse is the same thing, right? If I have a signal at F naught, then I modulate that, you know, with a cosine signal, and I move it back to the baseband, right? And it's a little bit more complicated because you also move it to other places. So you have to multiply by a cosine and a sine, and you combine things, and they cancel out, and you have the spectrum folded back to the baseband being around the 0 frequency, right? So you typically do that with ultrasound systems. We talked about that, I think, at some point, that the sampling of the data doesn't give you directly the RF, the radio frequency signal, that gives you the I and Q channels, you know. That's a little bit of trivia, but in any case, for this particular application, it just happens that you have it in baseband. So it's more convenient to look at that. So you would see that if there was something moving, you wouldn't have your spectrum or your frequency component at 0 hertz, but you would have it at a certain number of kilohertz. Typically, a shift would be in the order of kilohertz, which, interestingly enough, is the reason why you can hear the tone. Like if you ever watch a movie, or you had the experience, you know, to be there for somebody having an echographic obstetric examination, and like, here's a baby, you want to hear the heart beating? Okay. And there's a speaker, right? Usually in every echographic system, you turn it on, you crank up the volume, and you actually listen to something going, right? I mean, and the reason why you can hear it is because, and this is just pure coincidence, the Doppler shifts that we receive from vessels in the human body are in the audible range when you transmit signals in a megahertz range. That was pure luck, okay? Completely pure luck. It was not by design. So you can actually turn on a speaker and listen to it. And if you hear, you know, a frequency that's higher than some other, it just means that the blood is flowing faster, right? So if it's flowing slower, then you would hear, you know, a lower frequency sound. So it's just another piece of trivia information that maybe one day you can use in a bar conversation or something. So anyway, that's how you would do it. And this looks very nice and dandy, but it has limitations that we are going to discuss in the next lecture, because it's already 7:10. And I know that if it were up to you guys, you would stay, you know, the rest of the night talking with me about ultrasound and medical imaging and stuff, but you know, you have other things to do. So we'll stop in here. I see that there's a question in the chat. Yeah, I know. Yeah, I know. I mean, trust me, it actually works in the right setting. Okay, so so I'm going to stop sharing. Do we have any questions? Not about how you use that line in a bar, but just in general, you know, Doppler, like the things that we have been talking so far. Hopefully, this part of the concept is relatively easy to understand, right? I mean, based on the assumption that there is something flowing, which again is a blood, but you know that mainly it's a red blood cells, then you know that you're going to get signal that it makes intuitive sense that with the right processing, you would see that your spike in the frequency domain has shifted to a different location. And by measuring that shift, you know, with the derivation, the short derivation that's in your material, then you kind of can, you know, figure out what the blood flow speed is, right? Because you know the frequency that you transmitted, you know the sound speed of the tissues. You hopefully know, you know, what the orientation of the vessel is. Believe it or not, that was one of the things that led to uncertainties, right? With Doppler measurements. But I mean, you can figure it out, or you can even develop tools that would measure the angle and stuff. But if anything, you can look at it. And you can obtain actually a measurement of, you know, the only unknown in that whole bunch, which will be the velocity of the blood flowing, right? And of course, because it's a pulsatile system, then sometimes you're going to have, at some moment, you're going to have a higher speed and then a lower one, you know, and you could potentially track it, right? As you keep tracking how that Doppler shift keeps changing over time, okay? So hopefully that was relatively easy to understand. And it sounds like a great thing, just that it rarely gets to be used, and there are reasons for them, again, which we're going to discuss the next lecture. But do we have any questions about anything else that we have talked about today?
Yeah, maybe the second slide.
Sure. Let me
yeah.
go back to it.
Yeah.
So
there was
second slide.
the explanation on why the frequency has to be higher, like pretty high. So my question is, in the end, which frequency should we use for this?
So sorry, which so you're saying this one or which one? Sorry, which slide?
No, the second one.
I'm going to keep going. You tell me when to stop.
There.
Here.
No,
okay.
The next one. Yeah.
Next one. Here. Okay.
Yes.
Okay.
Sure. So
and the question was.
So in the end, which frequency should we use? Like the whole equation was pointing towards the reason why we should use higher frequencies, like than normal ultrasound.
Oh, but that in general, I mean, the question was motivated in general by, you know, I think it was motivated in the first part of the lecture, which is this echographic imaging in general, right? So the question was like, okay, so how can I, you know, just like there is IVUS or transvaginal or, you know, transrectal, are there any other things I can do that would be, you know, like physics oriented that would help me, you know, get higher frequencies from deeper within the tissues, right? And yes, we can, like harmonics and stuff. So for this, for example, for Doppler imaging, like how high do I want the frequency to be at? I guess it would really depend. I mean, it's basically in the end, because we're not going to be using continuous wave Doppler anyway, but I guess in the end, it would be the same thing. Pulse wave Doppler is what you would use. How high do you want the frequency to be? As high as you can in order to, you know, have a reasonably good depiction of the vessel that you're analyzing. Like if you're going for really, really small vessels, for example, of course, you need to be higher in frequencies. Typically, those are linked to, you know, more like, you know, superficial, like the vascularities, right? I mean, when you go deeper into the body, typically you won't be looking at really, really tiny things, because this is like your whole vascular system is like a tree branch, right? Yes. So you have something very, very thick, and then just the branches, and then it's thinner, and then you get to the vascularities. The more superficial ones is like thinner and thinner and thinner. But in any case, it really depends on the organ, right? I mean, if you're going to be looking at the carotid, for example, you can use a linear array. You know, you can use a relatively high frequency, like 10, 12, 15 megahertz. If you're going to look at the vessels in the liver, for example, it really depends. I mean, very likely you're not going to be able to pump more than, you know, like 3, 4, 5 megahertz, and that would be a lot. So it really depends on where the vessel is located at.
Okay. Thanks.
Sure, no problem.
And just another thing, just to remember that
sure.
The last lecture isn't yet posted in Paideia.
It is. Now
yeah?
It should be. Can you check?
Oh, okay. Maybe during the classes.
I don't know. Okay, can you check just in case?
Yeah, I will.
Sure. Awesome. While you check, do we have any other questions?
Yes, there is. Thanks,
awesome. No problem. Do we have any other questions? Okay, if you don't have any other questions, then I guess that would be the end of the lecture. And have a great night, guys. and see each other on Thursday, and then on Friday for office hour for the ones that can attend. Bye, guys.
Goodbye.
Thanks, teacher.
You
Thanks.
take care.